Good morning, everyone. I'm Xun from Coinbase Data Platform team. So today, I'm going to talk about how we build a Coinbase financial data ETL pipeline with the MongoDB Atlas Data Federation. This is also previously known as the data lake. A brief introduction of myself. So I joined Coinbase Data Platform team since February of last year. I needed the ETL and event-driven workflow area. Before Coinbase, I worked for Cruise, worked for Uber in the data infra area. I also briefly worked for Facebook and Microsoft for a few years. So for today's agenda, we will start with an overview of the financial data in Coinbase and also the ETL pipeline requirements. Then we'll take a look at the status quo before our new design. After that, I will go through the new design, the tunings, and the learnings in this process. At the end, I will have a few feature requests to the Atlas team. OK, let's take a quick look at the data in Coinbase. So to just give you a rough idea on the scale of the problem, so currently we have more than 98 million users with registered Coinbase account. We have more than 256 billion of assets on the platform across the retail and institution. And our service is available in more than 100 countries. So what kind of data we are dealing with here in Coinbase? So we know Coinbase is a crypto fintech company. So there are three types of data we are dealing with. So the first one is the blockchain data, things like the on-chain transactions, the blocks, the addresses, the wallets. These are all publicly available data. The second type of data is the product data. For example, we have acquired data from multiple marketplaces. We have user registration. We have user activities. This is very typical for anything with product and services. The third type is the financial data. This is actually a very mature area. Contains most of the private data. For example, user payment methods, transactions, balances, and accounting, tax. All this data is very important. So for today's talk, we are going to focus on the financial data. So why is it important? Financial data is very important for financial reporting. So every month, we have month-end closing. We have rewards calculation. We have earning release every quarter. And also, on a daily basis, we have core metrics calculation for things like daily revenue, monthly active users, monthly trade users, market share. This is very critical for product decisions. Not to mention, we also have other critical areas like risk, fraud, compliance. They all utilize and heavily depend on the financial data. So what's the ETL pipeline requirements for financial data? Here, I listed a few very important ones. The first one is the accuracy, zero data loss. So this is very obvious for financial data. Secondly, highly consistent. The third one, low processing delay. So our downstream always wanted the data to get into data warehouse for analysis as real-time as possible. Operational-wise, we would like the new ETL pipeline is easy to onboard new clusters, easy to maintain, and easy to debug when things go wrong. That's very, very important for our data platform team. We also want the ETL pipeline can scale up, can scale out. But what's the reality? Let's take a look at the status quo at the last year, at the Q2 of 2021. So in our production, we have this Lambda architecture, which means we have two ETL pipelines running in parallel. One is the snapshot pipeline. Another is the oplogs-based incremental pipeline. So both pipelines developed 4 years ago. So for the snapshot pipeline, right now we have a SLA of 2 days, which means after we take a snapshot of the Mongo database, it takes 2 days to get the data into data warehouse. And sometimes it takes more than 60 hours. For the oplogs-based pipeline, it's basically we detect the oplog change. Whenever there's a change to the document, we get it we get the document into data warehouse. It's very fast. The SLA is 3 hours. However, for this Oplox-based pipeline, sometimes it has data loss issues. That's the reason, actually, we set up this Lambda architecture so that we can sync data from the snapshot pipeline to the incremental pipeline to fix the data loss issues. However, we have to disable the sync last year, in the middle of last year, because the high delay in the snapshot-based pipeline.
Hi, June. Sorry to interrupt you. Hey, guys, I love the attendance here. If we could please have some of you come filter in. We have a lot of empty seats up here. We have about 6 seats up here, a few spots there. So if you all could please help me out and fill in some of these seats, that would greatly appreciate it. We still have a whole line outside of folks. So if we could just take 2 minutes to find a seat, that would be fantastic. Thank you so much.
Can I get another 2 minutes for my talk?
Thank you, June. I appreciate it. All right, June, please continue whenever you'd like.
Sure, thank you. Yeah, so this is the diagram of our Lambda architecture. So you can see the lower part is the incremental pipeline, and the upper part, the upper 2/3 part, is the snapshot-based pipeline. So probably you already get some idea how complex the snapshot pipeline is. It has more than 15 components. I'm not going to dive into each of them, but just give you this idea of the complexity. And for our design, we'll focus on this snapshot pipeline to make it fast, make it simple. So let's zoom into the snapshot pipeline a little bit to understand the data flow. So I actually did a summarization of the complex pipeline, and we have these 6 steps. It starts with this component called the DR Atlas. DR Atlas is used for disaster recovery. So in our production, every a few minutes, not every a few minutes, it's every a few hours, we will take a snapshot of the production database. We get the snapshot, then we have another 5 steps to get them into data warehouse. So the first step is the DR Atlas. We will copy the snapshot data from Atlas to an S3 bucket owned by Coinbase. After that, we have AWS data pipeline. It will start AWS EC2 instance and download the snapshot data to the EC2 instance. And then the third step happened on the EC2 instance. It has multiple sub-steps. We will first extract the data from the snapshot. Then we start a local MongoDB instance. And then we load the data into that instance. There are also some other small steps. Basically, there is a lot of things happening on that EC2. So we have to deploy a customized Airflow instance to the EC2 cluster to manage the workflow. So you can see this process is quite heavy. If you want to debug something, you have to find out the data pipeline, find the EC2 instance, and then log into that instance. And then you open the Airflow, you can see what happened. OK, back to the main steps. The fourth step, we have a whole bunch of Spark jobs to extract the data from that MongoDB instance, and then output them as a Parquet format. As the last step, we have an Airflow job. It will load the data into data warehouse. So just describe this whole process, I already get tired. So you can see, obviously, what's the problem. Yeah. So this old pipeline is very, very slow, and it's very hard to tune the performance. It has so many steps, a lot of redundant steps. And operational-wise, it's almost like impossible. It's very hard to get a new person to understand how it works, how to debug it. And it's error-prone because too many steps. So that's when we realized that this old snapshot pipeline is too outdated. We have to redesign it. So we talk with the Mongo Atlas support team. We sit together. We put all our requirements on the table. We evaluate multiple solutions. And at the end, we choose the Atlas Data Federation. It solves our problem and meets all the requirements. It's just based on two simple changes we did. One, we used the Atlas clusters. Second, do the server-side extraction. So let's take a look at how we do that two things. Utilize Atlas clusters. So this is actually a very natural choice because all our other production cluster is already in Atlas. So it doesn't really make sense to host a EC2 instance and then do a customized Mongo cluster there. It saves a little bit of cost, but the operation is crazy. And also, it takes forever to download the snapshot data from Atlas to the EC2 instance. This probably worked before when our data is small, but now it's already like too outdated. So we start to utilize Atlas clusters. So how do we do that? It's very simple. So for each of the financial cluster, we set up a dedicated cluster, and we use the same configuration as the production cluster. We call this the ETL restore clusters. And then when the snapshot is ready, we load the snapshot into the dedicated ETL restore cluster, and then we do the extraction from there for the ETL process. Server-side extraction. So before we talk with Atlas support team, we don't know that Atlas Data Federation provided this kind of server-side extraction. We used to just maintain our own Spark jobs extractors. So performance-wise, in my honest opinion, there's a big discount comparing to the server-side extraction. Because server-side extraction, we do batch operations. It knows the storage much better. It can do a lot of the deep optimizations that the client side will be very hard to do that. So after we utilize the server-side extraction, the whole operation of the client side from our side is much simpler. We just need to do two things. One, partitioning. The second step, Packeta. So for the partitioning, it's actually, let me explain it a little bit. So for the partitioning, it's allocate a list of workers. It will be based on the size of the cluster. Then we divided the whole document space into multiple segments. We assign one segment to each of the workers. So all these workers can work in parallel to finish the extraction process. The second step is the Packeta. Same as the meaning of the name. It's basically like do the extraction and save it in the Packet format. Atlas Data Federation provides a very good feature. It can allow flexible output locations. So we set the location to be the Coinbase-owned S3 bucket. This saves the extra round trip of data copy. OK, just based on these two things, the whole workflow becomes much simplified. So remember, in the older pipeline, we described that we have AWS data pipeline. We have customized Airflow on the EC2 instance. And we also have a production Airflow job. 3 workflow just for the older pipeline. Now, we just need to keep the last one, the production Airflow job. And it only contains 3 simple steps: restore, extraction, and load into data warehouse. It's much easier to maintain. And end-to-end, we measure the performance. It's 5 hours, including the snapshot step. Remember, we talked about the older SLA is 2 days, sometimes more than 60 hours. So that's a 10x performance improvement. I think it's pretty impressive, right? Thank you. OK, this slide is actually about the security design. I think it's less interesting. I'm going to skip it. But if you are interested, you can talk to me offline. And also for this one, the cost saving. People may think that this might be a very expensive solution, but we have a lot of optimizations. If you are interested, also talk to me offline. So I skip them just because I want to jump to this much more interesting part, the tuning part. So remember, we talked about the end-to-end performance, the new performance of 5 hours, right? It doesn't come for free. So we did a baseline run for one of our biggest financial cluster, the account activities. This cluster have 2.3 billion documents. the uncompressed data is 7.7 terabytes. So the baseline run, it turns out to be very, very surprising, 21 hours. So what's wrong? What's the bottleneck? So we look into each of the steps. The snapshot is almost always fixed less than 1 hour. The restore always takes about half an hour. And load the Packeta into data warehouse is also pretty much fixed, stable, half an hour. So the problem is the extraction step. Remember, we talked about there are 2 steps, partitioning and Packeta. Each of them actually take 9 hours. Total time for the extraction is 18 hours. So that's crazy, actually, I think. But it's still better than the original 2 days, though. So in the rest of the slides, I'm going to talk about how we reduce this 18 hours down to 3 hours. So the first thing we look into is the partitioning. So partitioning is basically divided the whole document space into multiple segments. So very intuitively, think this should be very fast, right? It takes 1 minute to do it, right? But now it takes 9 hours. It turns out that it's because Atlas Data Federation provides a very flexible choice. And we pick up the default algorithm. It's called a bucket auto. This is the algorithm that provided the most accurate calculation. However, it will load everything, all the documents into memory, and then divide them into multiple segments. So you can think about that. This kind of algorithm is accurate, but for huge database, it's very, very slow. So we get that 9 hours. So we did some tuning. We tried different algorithms. So the first one we tried is the random sampling. Basically, we pick up a few thousand documents, use that as an anchor point to divide the whole space into 100 partitions. So that actually dramatically improved the performance. We reduced it to 4 hours. It's still not that good, though. So we try to utilize the index. We do the index working. We do parallel index working. That can also reduce the performance, improve the performance quite a lot. So we get 1 to 2 hours of partitioning time. So in my opinion, this is still not that good because it's just doing the partitioning. It should be very fast. So that actually makes me to think maybe we are looking into wrong directions. So think about one thing. From a day-to-day basis, the distribution of the document, it shouldn't change that much, right? So based on that kind of understanding, we can pretty much use the partition result from the previous day. So we just memorize it and reuse it. That should be very fast. And also, we can probably just simply run the algorithm on top of the data we already get into data warehouse, because the data in data warehouse is already sorted. So if we run the algorithm there, it should be much faster. So we tried both. Both of them works pretty well. It takes a few minutes, or we just get it instantly based on the memorization. So with that, we simply saved 9 hours. The next thing we tuned is the Packeta step. So this is basically the things to do the extraction and then save into Packet format. So to help the understanding of this tuning process, I included the metrics dashboard of the Mongo cluster. So if you are familiar with this, you probably already identified a few problems. There are quite a few of them. So let's go through them one by one. So the first thing is the IOPS. If you look at this graph, you can see that the IOPS only reaches 4,000 per second. 4,000 per second, that's not very good for ETL process. So that's the reason, initially we take 9 hours, the major reason. So what's the reason we have such a low IOPS? That's because we simply copied the configuration from production. And in production, it's quite a different traffic. It's OLTP. Basically, the traffic is a large volume. However, it's random access. It's a pretty low throughput. But for ETL, we want a high scan throughput. So what we did is we provisioned more IOPS. So for this cluster, we provisioned 30,000 IOPS. And we can we easily improve the LPS. So the system can reach 20 to 30,000 LPS. So that easily improve the performance by 5x. So with this, we reduce the end-to-end time to around 5 to 6 hours. So it's still a little bit higher than our target, right? So something else is wrong. Can someone to identify what's wrong? Next. Okay, it's the slow ramp up. So if you look at this graph, it takes almost 2.5 hours to ramp up from 0 IOPS to the full IOPS we provisioned. 2.5 hours, that's too slow. So the reason is we load the snapshot into the restore cluster. It will take time to get it into the EBS volume. So what we did is we asked Atlas Data Federation to allocate more workers. So with more workers, we can push more random access to warm up the EBS. So with that kind of workaround, we can squeeze out another hour from the end-to-end time. But there's still something wrong. Any clue? So here, if you look at the graph, we have 3 verticals, right? That actually represent the 3 replicas. We have 3 nodes in the cluster. You can see that only one of them is doing the work. The other 2 is actually idle. So that's actually Atlas Data Federation bug. So we reported that to the team. The team is amazing. They got this fixed immediately. And after the fix, you can see all the workers is doing the job. Yeah, that also dramatically improved the performance. However, there's still something wrong. To save time, I'm just going to talk about that directly. If you look at the graph on the rightmost side, you can see there's still a read process drag forever, right? That's the long tail problem. So the long tail problem is some of the partitions probably get much more documents to process than the rest of the partitions. So majority of the work finished, 95% of the work finished, but this partition will drag forever. There could be multiple reasons that cause long tail issues. So today I'm going to talk 2 interesting cases we encountered. The first one is the skewed keys. So in our production, there's one day we suddenly find out that one cluster takes forever to finish, and we look at the output result. We find out that 95% of the documents all get into one partition. We dig into that a little bit. We find out that someone messed up with our production. They changed the key in a very bad way. While we are working with the production team to solve the key problem, so we did some workaround. We simply changed the algorithm to index working. So with the index working, we will go through all the document and divide that into equal segments. So that works pretty well for this small cluster. It takes probably, I remember it's less than 1 minute. If this kind of thing happened to the large cluster, my recommendation is to use index working plus memorization. There are also some other ways to solve this problem. If you are interested, you can talk to me offline. This is another case of the long tail. So what happened is, I think it's during holiday season, we have the production stopped for a few weeks. We didn't run the pipeline. And then we will run it again. We find out this kind of long tail issues. The reason is because we used memorized partition result, right? After a few weeks, the document distribution in the production is already quite different from what we have in data warehouse. So if you simply memorize something from several weeks ago, it doesn't work anymore. The way we solve this problem is we utilize the data from the incremental pipeline. Remember, the incremental pipeline, we have some data loss issue, but the data freshness is pretty good. So the data distribution in the incremental pipeline is very similar to the production. So we can just run the partition algorithm on a different set of data. And the problem solved. Okay, this is a tuning on the compression algorithm. I don't think it's that interesting, so let's skip it. Yeah, I only have a few minutes left, so I have to make it faster. This is the last tuning thing we did. I think this is the most important one, in my opinion. It's about the failure handling. So any system can go wrong. It can have failures, including Atlas data federation. So we saw network issues. We saw Atlas data federation go out of memory. We saw it reach the API limit. There are different reasons that it can fail. I think the failure is okay, but the most important thing is when failure happens, we shouldn't always restart from the beginning. If you restart from the beginning, all the progress will be wasted, and then you will double, triple, make the whole running time very, very long. So what we did is we divided the partitions into even smaller pieces, and we have more partitions than the number of workers, so that each of worker can have multiple units of work to do. And we also track the progress. So anytime one of the partition failed, that worker only needed to redo that small piece of work. So with this, we can dramatically reduce the average processing time. Yeah, this is very important. I want to emphasize. Okay, with all these tunings, this is one of the runs that I think it's a close to perfect run. It takes 3.5 hours. And this is a perfect run after further tuning. And for account activities, it takes 2 hours, 50 minutes for both partitioning and extraction. And I'm pretty sure we can push this further to make it even faster. But sometimes, the effort and the cost is a factor. So it all depends on how much you want to invest into this tuning. Oh, okay. This is the feature request to Atlas team. So I'm going to pause here. We still have 2 minutes. Any questions? Mm-hmm.
Couldn't you do bookmarks for individual workers so you could start where you stop from? Is that a possibility?
I guess we can have a feature request for the Atlas Data Federation team. They allow us to do that. For now, the query only allow you to start the whole piece of work. Yeah. Yeah. Oh, this question is pretty long. So when you talk about the offset, you mean the offset from each of the partition or something? Maybe we can follow up offline. Yeah. Okay. Yeah, that's actually also possible. In Coinbase, we started to use Databricks from later last year. I think this year probably is ready to apply some of the optimization using Databricks. Yeah. Yeah, it's possible. Any more questions? Yeah, go ahead. You mean MongoDB as a data warehouse, or? I see. That's a very interesting perspective. So right now in Coinbase, we use MongoDB as a production database, and we use Snowflake and the data lake for data warehouse. So I haven't think about this, but I think it's a pretty good opportunity. Maybe then we can talk about that. To see what's the chance of use MongoDB also as the data warehouse. Yeah. Yeah, of course. Which one is better? It's actually more depends on the use case, right? Depends on the data set, depends on the use case. Yeah, I think this is a pretty big topic. Let's catch up offline. Yeah, I'm also interested in this in that area. Oh, okay. Thank you.